Right now, let's look back at the animation that we have already viewed just now. So these two things that oscillate on both sides, that is sending the wave to the left and sending the wave to the right, they actually meet the criteria that the incident wave and the reflected waves having the same frequency, amplitude, and also the period. Okay, though it's not exactly the same, but it's good to simulate that. Okay, so they design the system in such a way that so that you can see all the three waves, as in the incident, the reflected, and also the combined one. Okay, so then we'll move on to the next slide to look at some of the specific points that I asked you to count just now. So this is the anti-node just now that I asked you to count, and then this is also anti-node, and this is the node. Okay, so at the anti-node we can see that the incident and the reflected wave, basically they rarely move from their position. So you can review or replay the video just now, and then you observe their position. So I give you the middle reference line there, so that you can compare the movement through times. Okay, so node and antinode. Antinode, you can see that if this is a trough here, it is actually because of the both waves, they are having a trough, so it add up. Okay, it add up, and due to according to the principle of superposition, it will give you a larger, or the addition of their displacement, and give you the largest amplitude there. Okay, so at any other instances, of course you would see that they are not formed from the amplitude, but they are formed from other displacement. So let's say a moment later this one arrive at here, and then a moment later, the same moment, this one arrive at here. So these two, they have the same displacement below the equilibrium position, and therefore they will also add up to a higher resultant displacement. Okay, so that's the constructive interference that is happening at that point there. Okay, whereas at the node there, whether it's this picture or the picture earlier, okay, this one is where both the waves, when they arrive there, they will give a destructive interference, or we say that, as let's say at this point, as it arrive here, so let's say it's positive 2 displacement, and then this one, as it arrive here, it give you a negative 2 displacement. Therefore positive and negative, they will cancel off. Okay, that's how the antinode and the node are formed. So in this animation, you will see also the slow motion of the formation of a stationary wave. So let's play that. So this is a string with one end fixed here. Okay, with one of the end fixed at this point, and then you can see the disturbance is coming from the right hand side. Okay, so this incident wave, those particles on the string is actually moving up and down. So this point moving up, then after that it reach here, then it move down. Okay, so the combination of those movement give you this wave. We already know that in the previous topic. And then as it reflected here, now you can see that it become big one. Okay, and then you see the blue color one. So blue color actually is indicating the reflected wave. Okay, as it moves through, then because of the interaction between the incident and the reflected wave, in such that it form those nodes and antinodes. Okay, so later we're going to show some snapshots of the particular moment where we can see how they add up and how they cancel off. Okay, so this is what you're going to see. At the back there, the incident wave and the reflected wave, actually they are continuously going to the opposite direction with the same frequency, with the same amplitude, with the same period, and so on. Okay, exactly the same wave. and because they are opposite direction, they give you this superposition, and therefore you get a stationary wave. All right. Okay, so this is some snapshots from just now showing you the moment where you see the whole straight line there. So how is this formed? It's because of the blue one and the red one. Those points on the string there, they are exactly I mean, the incident wave and the reflected wave, they are exactly cancelling off each other at this moment. Okay, and then we have the moment where it is slightly shifted away, that if you focus on this point here, okay, both the incident and the reflected wave, let's say they are 2 cm above the equilibrium, so they will give you a higher point here. Okay, whereas at the node here, this node here, every time when the reflected wave and the incident wave they arrive here, they will just cancel off each other. Okay, let's look at another instance. Okay, so the same node just now, so this is the node just now. Now the reflected waves is here and the incident waves is somewhere here. Okay, again, both of them are opposite. Okay, and then at the anti-node here, both of them actually are crossing with the same displacement, and therefore it adds up to be here. All right, and then here's a situation where you see the combined wave or the stationary wave achieve its maximum amplitude. Okay, it achieves its maximum amplitude. That's when both the waves are actually meeting at their peak. Okay, so this one here is still 0 because both of them are 0 now. All right, so at anti-node, both of the waves will interfere constructively because they are in phase all the time. They meet at the point always at the same direction of their displacement and also their magnitude. Okay, so we move on to see some differences between the stationary wave and the progressive wave. In the earlier topic we talked about the progressive wave. Now we talk about stationary wave, and let's put in some quantities and their properties to compare. All right, so first one, amplitude. Stationary wave it varies according to the position, 0 at the nodes and maximum at the antinodes. So all the points inside the loop just now, so I call this the loop, as one move up and then the other second it will be here. So this is like one loop, okay. I will use the word loop from here onwards. All right, so those position there, the antinode, the position of the antinode is having the maximum amplitude. Okay, that's the greatest of all at all time. Okay, except when this is 0 whereas for progressive wave, all the particles they have the same chance of reaching the same amplitude. Okay, though not at the same time, but they have the same chance to reach the same amplitude. That's the difference here that you can see. Frequency basically this will be the same thing. Okay, they vibrate in the same frequency as the waves. All right, except for the nodes because not moving, right? So wavelength, this will be distance between the pair of adjacent nodes or antinodes. So let me draw that. This is I'm drawing two loops that you see. Okay, when this one is up, this one will be down. Okay, so it move like that. Okay, later on it will be like that and then continuously. Okay, so it will be 2 times the distance between the pair of adjacent nodes. So this is the antinode, and this one is the other antinode. So once you find this distance, you times 2, that will be the wavelength. Okay, or straight away we can see that from here to here there's one wavelength. Okay, actually because this one will be the whole wave at that certain time. Okay, the other side of it where I always draw with the dotted line, right, is the position of it after a while. Okay, that's after a while. Whereas distance between two adjacent particles which have the same phase, that's for the progressive wave. So progressive wave, we say that. Okay, so this one is the wavelength. Adjacent particle having the same phase. So these two having the same phase. Okay, so we don't say that in the stationary particle, though this is the peak, right? Okay, or the maximum amplitude, but it's actually happening later. Okay, actually happening later. So it's called the antinode, but that antinode or that achievement of that position is actually later, not at the same time. Therefore, we cannot take that as the same one wavelength. Okay, one wavelength is actually two times of it. Okay, this is the part that always confused. That's why I go a bit more lengthy to explain about this. Okay, phase of all the particles in between the two adjacent nodes is the same. So what is meant by that is, so again I draw that, and this is a moment later. Okay, so there are two loops here. So all those particles that I try to label here, actually they have the same phase. Okay, so all these have the same phase at this moment. I mean at any point of the time. Whereas at any point of the time, those that are on the other side, okay, in the adjacent loop, when this one is moving down, right, all this will be moving up. They will be always opposite in direction, and therefore their phase difference will be always pi radian. Okay, remember the concept of phase difference. So they are always half a cycle in difference of their phase. Okay, all particles within one wavelength have this different phase. So again, I draw this wave here. So all these points, they will have a different phase. Okay, for example, this point and this point has a phase difference of pi radian. This point and this point, these two, they will have the quarter of a wavelength, as in pi over 2 phase difference. So all the points, they have a different phase difference. All right, whereas in the stationary wave, inside the same loop, they all have the same phase difference. Okay, same phase. Waveform or profile of the wave, stationary wave, it doesn't at once. It will just move up and down there, that you don't see it travel to the left or right. Whereas for progressive wave, it does at once with the velocity of the wave. It travel, the profile move because of the synchronous oscillation of the particles. Energy, there's no translation of the energy, as in there's no travel or propagation of the energy. Is always just inside the loop there, up and down, changing up and down there. Okay, whereas for progressive waves, it's actually propagates in the direction of travel of the wave. All right, so next video we're going to show how stationary waves will be formed in different situations. Okay.